day we've all been looking forward to.
A little raw meat here. Okay, let me. I know.
I'll get that
I'm
over
going
there.
to.
Yeah.
So let me start by observing that we currently have 15 minutes of negative slack, and I am scheduled to speak for 15 minutes. And I'm not going to help one bit. All right. Also, I'm about to do something I despise, which is read the charts, or more or less read the charts. I hate charts like that, but so many people are following what we're doing right now just by seeing the charts, not by seeing the presentations. I have to do that. Okay, first chart. Oh, do I have a clicker here somewhere? No. You have it right there. Ah, very good.
You're going to tell us how to go to Mars. You can't find the clicker. I don't know.
I'm going to tell you how not to go to Mars, and I cannot find the clicker. All right. Let me start.
Well, Mr. Sherman, he has a Caltech degree.
That's right. The other technical school. Let me start by describing how we see our interface to the great work that Bo's group has been doing. Clearly, the question of how we're going to leave the Earth is tightly linked, I might even say dominated, by the question of what we do when we get there. If you don't know what you're doing, anything will work. The problem is very complicated. There are many options. You can't necessarily all pick one from column A and one from column B. So to simplify the problem, we have decomposed the question of what the launchers are into broad classes of boosters that in incredibly rough terms we think of as 25 metric tons, 75 metric tons, and 125 or larger metric tons. That's the useful mass placed in LEO. You got to be very careful with your bookkeeping because a lot of these systems use the Earth departure stage as the final stage of the launch vehicle, and there's the question of, okay, how much of that is part of the launcher and how much of that is part of the payload? Some of these members of each class of boosters might or might not be used as crew transport vehicles, given appropriate measures for the booster, like the launch escape. That forms an independent axis of the trade, although not all of them are that interesting. It's also possible that we might not employ any of the large boosters as crew transport vehicles. It's quite credible to consider turning all crew transport over to a crew taxi capsule, which is not what you leave Earth orbit with. That allows you to launch the crew on something more in the 9 metric ton class, and in that kind of a scenario, something like Orion could be launched unmanned and the crew brought up separately. That leads to the question of human rating and crew safety, on which a lot of words have been spoken inside the subcommittee as well. It's not a secret how you get low loss of crew. You combine a highly reliable launch vehicle with an adequate emergency detection system that tells you when it's about to have a bad day, in time to trigger an escape system, a launch abort system that gets you far enough away from the vehicle to survive the bad day, with as few ideally as possible, or ideally no black zones in which you wouldn't dare pull the abort handle. It's also obvious that different launchers have different characteristics that require different launch escape systems. I will note in passing the issue of dynamic pressure. It's a significant driver, how hard you're smashing the air at the time that you want to try to get away. NASA has recently developed some new human rating standards. I think that's an encouraging process to see them going through. Those standards do appear to embody reasonably good practice for a new design. They're mostly an adaptation of received wisdom for how would you do it if you were doing it today. However, since no prior NASA manned launch vehicle, nor Soyuz, appears to meet these standards, we got to be careful that we don't take our desire as required. And therefore, it's our opinion that where there are existing or derivative launchers that meet the intent of the guidelines, they should be giving due consideration as true transport vehicles. There is data that shows that government's independent mission assurance process does improve booster reliability. This is one of the many Nixon goes to China moments in this presentation, because there's a few things that I have said in the past that I have changed my mind about in the course of this process. and there is good data out there that shows that. There are many customers in the government that go through this mission assurance process successfully. The Air Force, the National Reconnaissance Office, and NASA itself in the Launch Services Program. And all of these are customers that launch billion or multi-billion-dollar flagship national missions. And this really speaks to the question of, what would you do if you knew how to make the booster more reliable? And you want to do that for the crew, why wouldn't you have done that for the multi-billion-dollar national security mission of which we're going to launch one in 20 years? And the answer that we get back from people who do boosters is you wouldn't. If you knew how to make the booster more reliable for that class of mission, you would have done so. Therefore, because there are boosters out there that have gone through this kind of process, it's possible and an option well worth considering that providing an Atlas V 402 class launcher as a government-furnished launch service to commercially supplied crew taxi capsules might provide a faster path to getting NASA acceptable levels of mission assurance for those capsules, and therefore might present an option to pull in some elements of closing the gap. Finally, to everybody watching this process and to people within and without NASA, I have to say again more lengthily what I've said in questions. You have to use extreme care in interpreting probabilistic risk assessments. Over 90% of historical launch vehicle failures, and that's actually, I'm being understated, are from causes that are not modeled by probabilistic risk assessment. Things like the design's not right, the environment's not right, the testing didn't test what you thought it did, somebody plugged the connector in backwards, that kind of stuff. Therefore, first, probabilistic risk assessments are always much better than demonstrated reliability of a launcher, and will always be. And furthermore, because 90% plus of what you're going to fail from isn't even being captured in the process, assigning multiple significant digit significance to your probabilistic risk assessment is silly. At best, it tells you this is a lot better than that when you're comparing paper systems. Here's one of my action items from the chairman. Never let it be said we're not responsive. It is often said, and we have heard many times on this commission, that if you want to go beyond LEO, you got to have a big rocket. I don't think that's right, and the consensus of our subgroup is that's not right. What should be said is to go beyond LEO, you got to have a big Earth departure stage full of propellant. Now, if you choose to launch that wet or mostly full as a single large launch element, that does imply a very large rocket for going to the moon. And if you're going to Mars, it implies a very large, I'm tempted to say improbably large rocket. Alternatively, if you launch a lot of little EDS stages and gang them together in some fashion, you can solve that problem, but it becomes a very large in-space assembly problem. It's been compared to sending ISS to Mars every time that you fly. And it becomes very unwieldy in the larger systems. There's a significant mass penalty for the smaller tanks that are all ganged together. The third way is if you launch a lightly loaded, or in the extreme case, dry Earth departure stage that does require the ability to transfer propellant, and later in the exploration architecture to store propellant for extended periods of time in space, you can now do much larger missions with the same size booster. That technology has also been called a depot. There are no new ideas in this business. I appeal to St. Werner that this is actually what he had in mind. This is how he wanted to go to the moon. He called it tanker mode. And he wanted to go to the moon this way because he knew if we went to the moon this way, we would have been on Mars by now. But we didn't, and we aren't. So let's see if we can fix it. Because of the question of the chairman, I will spend a little more time than I'd planned on why propellant storage and transfer is such a big deal. It really is a game changer in Earth-to-orbit transportation to have this capability. It decouples the size of space systems from the size of the launcher to an extent. The large launcher has driven the development and, much more importantly, the sustaining cost of exploration programs since the Apollo era. We still do face the problem that you have to launch what we're calling the biggest, smallest piece in one piece. You know, this small launcher idea, there's a threshold past which it gets silly, and we aren't sure quite where that threshold is yet. What we are pretty sure is that 75 metric ton class vehicles are above that threshold. We're not at all sure yet, and again, this is Nixon goes to China. I came in absolutely convinced that 25 metric ton vehicles were big enough to launch all the pieces. I am by no means convinced of that today. However, the majority of mass launched in any architecture that we see is propellant. And that can be launched in any size launcher, and it is not a high value payload. We have spare oxygen. Therefore, the canonical charts that many people have seen that say you can never have many launches in your architecture because, you know, if they all have an N% chance of fail when you do Y of them, it's N to the Y chance of the thing not working at all, that chart's not right. Because while you don't have spare crew and you don't have spare Earth departure stages, you do have spare propellant. And you simply get in the mode of saying, I launch a lot of propellant, and if I lose one once in a while, that's okay, the next one's coming up next Tuesday. This allows the widest possible competition in Earth to orbit launch, and it allows significant involvement by international partners. We believe it will stimulate greatly an expanded commercial market for launch. It may, if coupled with a significant exploration effort that needs a lot of propellant, finally provide the steady, reliable, large payload for raw mass in orbit that's been the missing piece for doing a commercial reusable launch vehicle. We have surveyed many NASA and industry experts. There appear to be no significant technical barriers to on-orbit propellant storage and transfer if you use settling acceleration during the transfer. There are other approaches that don't require settling acceleration. They're very interesting, but they are at lower technology readiness level. But that does not to say that we don't need flight demonstrations and technology maturation efforts. These things are generally in the TRL 5 to 6 category right now. There is work to do. And there has always been work to do, and no one has ever done it, and that's why we never do it, in a nutshell. Also, this whole notion of changing over to an architecture that has a high flight rate of small vehicles component is a very foreign way of doing business in this country. It's not at all a foreign way of doing business, for example, in the way that Soyuz was developed and operated. But to us, this looks new and scary and different, and no program ever wants to do the new and scary and different because that's their career on the line. So I'm up here saying it instead. Also, this would have been unthinkable as a rational option before the International Space Station and before DARPA's Orbital Express mission. 20 years ago, in-space operations, in-space docking, certainly autonomous docking, certainly propellant transfer all seem like scary things. We have now done all of those things. Some of them we do every couple of months. Just a quick flip chart provided by some of our partners on pictures of some of the key technologies, just showing you these are generally not view graphs. These are generally pieces of hardware being demonstrated in the labs. The one obligatory rocket science graph provided by Ed Crawley, and thank you. I will summarize this in words. It is an eye chart. If you launch your Earth departure stage with the payloads that you plan to carry, tanking in orbit gives you a roughly factor of 2 potential improvement in throw weight to trans-Earth or trans-lunar injection or trans-Mars injection. If you launch the EDS as a standalone element, bring the payloads up separately, the EDS can be very, very large in comparison to its mass on the way up. You then become limited by the fairing. We're still studying, and our NASA colleagues are helping us study the fairing limitations, but it looks like you can get a 6 or 8 multiplier on the throw weight of the size of your booster that way, which if you're thinking about going to Mars is getting really interesting. In-space transportation, to address the other action item. There are a lot of options. The baseline is always chemical propulsion, because that's what we got. The original baseline, of course, was all propellant comes from the Earth. We want to challenge that. You can start, and as you go down this chart, you're starting to change the game on how much additional technology you insert. You can add propellant depots in other locations beyond LEO. That, in turn, fosters the possibility of doing in situ propellant production in other locations beyond Earth. And that, as Ed said, cheats the rocket equation, because now your whole mass rate, instead of multiplying two large numbers to each other, you only got to pick one of the large numbers, you pick up gas on the other end. Beyond that, there are many options for advanced space propulsion. This has been the holy grail of what you'd like to do if you wanted to go to Mars for a long, long time. It is a big ticket item. I'm going to speak a little more about it. This is the one takeaway from this section I want to give is there's a false dilemma that people get into saying, well, we got to do a space propulsion, but it's going to cost a fortune and it's got to be nuclear and nobody's ever going to let us do it. It's not obvious that it has to cost a fortune. It's not obvious that it has to be nuclear, but the people who are working on these alternatives are doing it in shoestrings in colleges and laboratories of individual people. They've essentially got no money. And if we don't like the same answer always coming out, we better change the question. With chemical in-space propulsion, clearly this all revolves around some kind of Earth departure stage. We have defined for NASA to give us additional data 3 Earth departure stages that simply map to the 3 classes of launch vehicles that I discussed earlier. In the case of the 25-ton case, it's obvious that the EDS launched dry is the only competitive alternative. You can just barely think about doing the mission with a 25-ton anyway. You certainly can't do it if you compromise. Therefore, a 25-ton vehicle would require a depot right from the get-go. You can't go anywhere without one. The 75-ton class vehicle, we're defining an EDS that will support some initial exploration missions in what we call top-off mode, where one EDS transfers propellant to another, but you don't yet have a depot. You will still need a depot, but it can come in a little later in the architecture. And with the 125-ton class, you can do everything you want to do on the moon without a depot, and the depot comes in when you start thinking about going beyond the moon. Running late on time, so I will pass more lightly over this than I'd wish. But let me just say that as a result of and since Apollo, we have learned a lot more than we knew in 1962 about the places in the solar system, what you can get there, and there isn't any place we're interested in going that you can't get propellant of one kind or another. There's differences in the amount of equipment that it takes. There's differences in the kind of equipment that it takes. Nobody's done flight demonstrations of any of this yet, but it's in the category that I as an engineer refer to as just work. In some cases, it's just a lot of work, but no miracles required. This clearly requires the same kind of propellant storage and transfer technology. There's no point in making gas on planetary surfaces if you can't hang on to it and pump it from place to place. This also leads to the possibility of a cis-lunar depot, which turns the moon from an interesting place that you visit along the way into our first mining outpost in space. You bring the propellant that you store not initially just to help the moon transportation architecture, but as you make more and more of it, you start exporting it up to L1, and now the Mars guys can buy it from you. This is a chart I wish I saw NASA produce more often. It's what in the semiconductor industry we used to call a technology roadmap. In the semiconductor world, we routinely, our entire business depends on the assumption that 10 years from now we will have technologies that we have no idea how to do, but we're going to boldly go forward assuming we're going to figure it out along the way. But we don't just hope and pray. We list how we might do it. We pick out a couple of leading candidates. We fund real technology programs so that by the time we get there, we have what we need. The takeaway message that we took as a subcommittee from DRA-5, it's a great piece of work on how you might go to Mars with current and easily visible near-term achievable technologies. The takeaway message, at least I personally took away, is we're never going to Mars that way. Not because it couldn't be done, but because it shouldn't be done. We shouldn't go to other planetary bodies at what I call $1 billion per footprint. Because we won't stay. It'd be Apollo all over again. We'd go and we'd do it a couple of times, and the next election would come and somebody would say it's too expensive and we should stop. If we want to go for real, we got to go in a more affordable way. If we want to go in a more affordable way, we got to start working on the technology to do it. I want to call out particularly the cosmic ray issue. It's something Chris and I have talked a lot about. It really hasn't received enough attention as a rate limiting factor on human expeditions to Mars. There are two classes of ways to deal with it that we know about already. But we know much less about this phenomena than we should. You know, for a phenomenon that might be the limiting factor on human transport to and from Mars, the amount of resources being paid on studying and understanding this and even figuring out is it as bad a problem as some people think is laughable. It's sometimes said that, well, there's nothing we can do about it, so why study it? That's not true. There are things we can do about it. Cycler HABs are a possible way of doing it, because, and that, for those who don't know, that's an architecture where you don't launch the HAB every time. It just sort of stays in a permanent free return trajectory, and you ferry the crew to and from it. And although it's expensive, it's at least possible to think about making those things massive enough that they could provide shielding from galactic cosmic rays. But, you know, we should be working on that. But for every dollar we spend on that, let's at least spend a dime on figuring out whether it's a problem or whether there's biological countermeasures that we can take to do something about it. Last, this my get off the stage chart, is changes in the business model are at least as powerful as changes in the technology. We have heard a lot of stories from a lot of people laboring mightily in the trenches of NASA to do the impossible. And we got to be clear to all the national policy stakeholders that changes in how we specify and acquire and operate systems and in what NASA is allowed to do in that respect have as strong an effect as technology on what we can achieve for a given budget. NASA is constantly asked to do more with less. Now, at some point, no matter how clever you get, it ain't enough. And if NASA is going to do more with less, without exactly saying how much or how little, they have to have, for example, the flexibility to adjust the size and composition of their workforce and their facilities to the job that they've decided to do, whatever that is. Furthermore, if you want to get the maximum leverage from what the commercial sector can do, you have to be able to make commercially bankable commitments to future purchases. No one today is going to loan a company money to develop a NASA system on the grounds that NASA will be a future market, because no one can predict what NASA will do in the future any more than NASA can predict itself what NASA will do in the future. But there are mechanisms that other government agencies have to do things like loan guarantees that NASA currently does not have, that Congress could change, that would give it the ability to make future purchase commitments in a way that would stand up. And the converse of this is true. If NASA can stand up and present credible markets, you will no longer have to develop everything yourselves. People will do it with their own money, hoping to make it back from you in the future. Finally, NASA should be the source of research and development, the source of technology maturation, the source of system requirements, the designer of the architecture. NASA should not primarily be its own supplier. There are a lot of, and I want to say a word about why that is. All programs, public or private, face a critical problem of distinguishing between what I call desirements and requirements, or mission creep, or call it what you will. There's always limited resources, there's always limited time, there's always unlimited things that you'd like to do. A separation between the people who decide what we want and the people who decide how much we can afford, and the people who decide how we're going to do it and are responsible for doing it, is critical to helping to manage that process. And that's not unique to NASA. I've seen the same thing in other environments. Now, there are many tools available to NASA to do this different way of doing business. They can do straight purchase if the service exists. They can do Space Act agreements. They can do COTS like cost-sharing arrangements with private industry. They can do fixed-price contracts, which I think of as a risk-sharing rather than a cost-sharing mechanism, in which the private sector might not, might be willing to commit the resources to handle any overruns, but not necessarily able to commit the resources for the initial purchase. There's prizes if you want out-of-the-box ideas. I'd love to see some of those on this cosmic ray question, because there's a lot of room for creativity there. There's a lot of things we can do. Let's go do them.
Jeff, thank you very much. I think you covered our action items, so why don't we go ahead and we'll pick up any questions at the very end.